Today we'll discuss Gaussian integral, which is also known as Euler-Poisson's integral. Now it is named after the German mathematician Carl Friedrich Gauss, and it is expressed as integral from minus infinite to plus infinite e to the power minus x squared dx, which is equal to under root of pi. Now since we have already discussed curve tracing in previous videos, so if we look at the function fx equals e to the power minus x square, we know that if I replace x with minus x, equation will remain the same. So that is, it is symmetric about y-axis. It will be continuous and differentiable. It will intersect y-axis, that is when x is 0, value of y is 1. So at 0, 1. So if I'll differentiate it also, if I'll find f dash x, I'll get e to the power minus x square into minus 2x. If I'll put it equals to 0, I'll get it 0. And then at 0, rightmost is plus, then it is minus. So it'll take a local maximum at x equal to 0. And the local maximum value will be simply 1. Now if I'll find limits also, limit x tends to plus infinite, e to the power minus x square. So there'll be e to the power minus infinite, and e to the power minus infinite is simply 0. So if I look at all these characteristics, then I can draw the graph of e to the power minus x square. So now I'll draw the axis. So that's your x-axis and y-axis. Now about this graph, it will be symmetric about y-axis. It will intersect y-axis at 0, 1. It will have local maxima at x equal to 0. At minus infinite and plus infinite, it will be 0. And then it will be symmetric about y-axis. So with all this information, now we can draw the graph of e to the power minus x square. Now this Gaussian integral is nothing but area under this curve and x-axis. So basically we are looking for this area. So now we need to prove that this area is equal to under root of pi. Now Gaussian integrals, they are closely related to error function and normal distribution, and they are also very frequently used in quantum field theory. Now there is no elementary indefinite integral for it, but the definite integral, it can be evaluated. One of the standard way to compute the Gaussian integral was given by Poisson himself. So his idea was, I can express this integral as I, and I can write it as from minus infinite to plus infinite e to the power minus x square into dx. I can also write this integral as from minus infinite to plus infinite e to the power minus y square into dy. Now basically in a definite integral, if the function is same and the limits are same, the value of two integrals will be same. So basically y here is a dummy variable. Now I'll multiply the two integrals. So if I'll multiply them, I can write it as I square, and it will be from minus infinite to plus infinite e to the power minus x square into dx, and then into from minus infinite to plus infinite e to the power minus y square into dy. Now from multivariable calculus, I can write it as double integral from minus infinite to plus infinite, and then again from minus infinite to plus infinite, it will be e to the power minus x square into e to the power minus y square dx into dy. So I'll express this integral as I square from minus infinite to plus infinite, from minus infinite to plus infinite, and then it will be minus x square plus y square into dx and dy. Now how do we solve this double integral? In order to solve this integral, I'll change this integral into polar form. So what I'll do is, I'll write x as r cos theta, and I'll write y as r sin theta. Now in this integral, the differential dx into dy, it represents an element of area in Cartesian coordinates. The element of area in polar coordinate is given by r dr into d theta. So here this factor of r is the Jacobian determinant, which appears because of the transformation to the polar coordinate. So what I'll do is, now I can write this integral as I square, and then these double integrals it will be e to the power minus x square plus y square will be simply r square. And then in place of dx dy, I'll write it as r dr and d theta. Now we need to put in the limits also. Now in order to cover the entire real plane, so the value of r should vary from 0 to infinite and the value of theta should vary from 0 to 2 pi. Now I can split these two integrals. So now I can write from 0 to 2 pi d theta, and then from 0 to infinite e to the power minus r square into r dr. Now this first integral, it is very simple. It is simply theta, and then I'll take the limits from 0 to 2 pi. Now what about the second integral? Now the second integral is again nothing but a simple integral which can be solved by substitution. So in the second integral, what I'll do is I'll take, let r square be z. Now I can write r dr as 1 upon 2 dz. So I can change this integral as e to the power minus z into dz, and then I'll have this 1 by 2. Now when r is 0, z is 0. When r is infinite, z is infinite. So I can write 1 by 2 e to the power minus z upon minus 1 from 0 to infinite. So I'll write minus 1 by 2 e to the power minus infinite minus e to the power 0. Now e to the power minus infinite is 0 and e to the power 0 is 1. So I'll get this value as 1 by 2. So I'll put the value of this integral, which is 1 by 2, and here I'll get 2 pi. So 2 pi into 1 by 2 is simply pi. So the value of I square is pi. That is, the value of this integral is simply under root pi. So this is how we can prove that the Gaussian integral of e to the power minus x square from minus infinite to plus infinite is under root of pi. If you like the video, consider subscribing and sharing it with someone you know who might benefit from it. Also, the best way to navigate any topic is through a playlist. Simply go to the channel page, click playlist, and select the topic you wish to study.